Okay, so number 2, we have a limit problem, and we have the limit of x over e to the 2x minus 1 as x approaches 0. And ultimately, if we put a 0 in there, direct evaluation here, we would wind up with 0 on top. E to the 0 is 1, 1 minus 1 is 0. So ultimately, it's an indeterminate form, so therefore L'Hopital's rule. So this would be a VC problem, so L'Hopital's rule. And so if we take the derivative, then we'd have 1 on top, 2e to the 2x on the bottom. And derivative of the top is 1, derivative of the bottom, 2e to the 2x. Plug in 0 now, we'd get 1 over 2 times e to the 0, which would be 1 over 2. So ultimately be a half, which is letter B. Questions on that one? Anything else, 1 through 4? 5 through 8? Alright, number 6, we have a table of values given, some values of the function, some of the derivative, and it says the derivative here is continuous on 0 through 5, and ultimately we want to know what is the value from of the integral from 1 to 4 of f prime x dx. Okay, so if we have this derivative curve, if you will, and we want to know what is the area underneath it from 1 to 4. Ultimately, we can, if we use the fundamental theorem here, our antiderivative would be just f, wouldn't it? And so if we evaluated that on 1 to 4, we do f of 4 minus f of 1. F of 4, according to the table, is what? 2. And f of 1 is negative 5. Means we get 7. So ultimately that'd be an AB problem. The fundamental theorem of calculus. Questions on that one? What else? 5, we got a particle moving along a straight line, so the velocity is given by v of t equals t squared. And the question is, how far does the particle travel between time 1 and time 3? Okay. So remember, ultimately here the distance traveled when we have a velocity curve is the area under the curve, but remember, if it's a negative area, it has to be treated as positive, which we can get done with the absolute value of v, if you will. I guess it's our total distance. So for us, since we don't have a calculator here, we can't just write the integral and then put it in the calculator and figure out what it is. So ultimately we got to look at that function, though, keeping in mind, though, that this function on any interval here is going to be positive valued. So do we really actually need the absolute value in this case? You know, the area under the curve from 1 to 3 will do it, won't it? So if we rewrite our integral from 1 to 3 of t squared dt, and again, it's going to be positive valued, so the negative part is irrelevant. It's going to be our distance traveled. It's going to be given by that, and so if we find the antiderivative, t cubed over 3, evaluated at 1 and 3, we get 27 over 3, which is 9, minus a third. It'll be 8 and 1/3. 5/3, and I'm missing 1 here. Yeah, that's not a choice, is it? Time 1, time 3, what am I missing? Where's that? Yeah, but it should be, oh, never mind, my adding skills. 8 2/3, not 8 1/3, that's why the 26 threw me off. I was thinking 25/3. Ultimately it should be 8 2/3, 26/3. See, all the calculus looked right. Add correct, subtract right. Questions on that one? through 8. Okay, at 7 we got another slope field. Again, keep in mind this would be just an AB problem, the previous one. BC problem here with the slope field. Nope, I lied. Slope fields are AB. They used to be BC, or they used to. So bottom line here is with our given slope field in our picture, it's a slope field for a differential equation. It's given in terms of y here, and the question here is about this function y. But again, keep in mind that we're looking at a picture of a derivative function, if you will, here. We don't know an initial condition here, so we don't know which path that it actually follows on that slope curve. But if we look at the choices that we have here, it says if y of 0 is greater than 2, then the limit as y approaches infinity, okay, is going to be approximately equal to 2. So if you look at the again, if you look at the slope field for y of 0 greater than 2, keeping in mind we're talking about the y values being greater than 2. So if you look above the line that we have 2, and if we look at the limits of the y values, okay, the question is do they approximately equal 2 here? Okay. Well, keep in mind though that when in the notation that they give us in the second part of the sentence, we're talking about y of x, which is ultimately like f of x, right? And we're letting x go to infinity. So as x gets bigger, okay, do the y values approach 2? Okay, if you look at the way that curve is, put it on here a second. If you look at the way the curve goes as we go to the right, when we're above the 2 line, if you will, okay, this again meaning above the line y equals 2, if you will, as we go towards infinity, what seems to be happening with any curve that we were to draw in here, they're all getting closer to what? They're getting, it looks like that's a horizontal asymptote, doesn't it? Okay. So it appears that 1 would be true. Let's see about number 2. On number 2, it says if we have y values that are between 0 and 2, then the limit of y of x is also 2. Okay? So we're looking at values between 0 and 2. Question is, as we let x get larger, okay, do the y values approach 2 also? You know, ultimately, it looks like if you look at just from the tops and the bottoms here, it looks like these are that 2 is an asymptote behavior on both accounts. It's pretty much the same behavior above as it does below, right? All right, and then let's check and see about the last one, the y values here for less than 0, which ultimately is this group right down here. Question is, as we go to infinity, does it approach 2? Okay. What seems to be happening with the y values as we go to infinity here? Anywhere below the x-axis, in other words. Okay. Do these appear to be going to 2? These appear to be going down, don't they? Okay. So ultimately, it looks like we're going to go with 1 and 2, which would be letter D. Again, bottom line is this one we're talking about the stuff that's above the line y equals 2, what appears to be happening as we're going towards infinity here in the x direction. The y values look like they're going towards 2. It appears that this is a horizontal asymptote, okay, not only above it, but also below it, so between 0 and 2. But then again, anything below this, it looks like the values are going not towards 2, they're going down that way, okay, which is definitely not where 2 is. Alright, what else? Alright, let's take a look here. Ultimately here on number 9 we have the derivative of the natural log of 1 squared minus 1 equals. Alright, so if we want to find the derivative of a natural log function, we need to know the general rule is that the derivative of a natural log of u is 1 over u times the derivative of u. So in our case, we'd write 1 over 1 minus x, 1 over x squared minus 1. And then we'd multiply that by the derivative of 1 over x squared minus 1. So somewhere over here I'd probably write the x squared minus 1 as a power function. Use the chain rule. Ultimately wind up with that. Negative 1 times the argument, the negative 2 times 2x. We'd wind up with negative 2x, and then x squared minus 1 all squared on the bottom. And keep in mind that goes here. Alright, and then with this situation right here, 1 over this is just the reciprocal of this, if you will. So with that said, if I take this expression over here, some more space, we'd have x squared minus 1 times negative 2x over x squared minus 1 all squared, which ultimately that would go with one of these. We have negative 2x over x squared minus 1. Looks like that is not an option, but remember, if you look at choice B, if we were to multiply the top by negative 1 and the bottom by negative 1, get it on the screen here. If we had this, that would be equivalent to this. We made the top, we multiplied by top and bottom both by negative 1. We could make the top positive and the bottom would be, the opposite of the bottom would be just those two switched, subtraction. So letter B. Alright. What about anything up to 14 at this point?
12.
And 12, we have the equation of the line tangent to the curve y equals kx plus 8 over k plus x. Because x is negative 2. Oh. So at this particular point, the tangent line is y equals x plus 4. Okay. So this is the tangent line at that point. And bottom line here is what is the value of k? Well, keep in mind that if this is our function, and we have a tangent line of y equals x plus 4, then we know that ultimately this derivative right here at negative 2 would have to equal what? Slope of the tangent line and the derivative have to be equal, don't they? So what's the slope of the tangent line? 1. So that means the derivative of this at negative 2 would have to equal 1. Okay, so ultimately it's the AB derivative problem. So let's find the derivative then. If we find the derivative of the function, we got to use the quotient rule. So if we had k plus x, which is the bottom, times the derivative of the top, minus the top, times the derivative of the bottom, all over the bottom squared. So in bottom, derivative of the top is just k, it's linear. Top is that, derivative of the bottom, k plus x. Again, k is a constant, derivative is 1. And if we simplify, we're going to wind up with k squared plus kx minus kx plus 8. Which ultimately would give us k squared plus plus 8, that is. Kx is be gone. K plus x all squared. And we essentially want to let that equal 1, but we want to let that equal 1 when x equals what? When x equals negative 2 from above. So ultimately we'd have k squared plus 8 equals k plus x all squared. Plug in my negative 2 there. And if I add that, k minus 2, and the only variable here is k, so I just need to solve this quadratic equation. Make sure you don't get hit by a train and just square the inside and outside here, so make sure you got minus 4k in the middle, plus 4. Expand that. And then conveniently the k squareds, if we start putting this stuff on the same side here, are going to be gone, so we're going to wind up with negative 4k over here. And actually, since it's linear, we'll just get that over on the side, so we don't have a 4 there. So negative 1 would be our k. questions on that one? What else? 14. Okay. And the 11 says we have a function f is continuous on the closed interval 4 to 6. It's twice differentiable on the open interval 4 to 6, and we know that the derivative at 5 is equal to negative 3. We know that f is concave down on the given interval. And the question says, which of the following could be a table of values for f? Okay. Alright, so checking out our choices here. Again, knowing that we have f is a continuous function, keeping that in mind. It's also twice differentiable. That means it has a derivative and a second derivative. And out of our choices here, we know the derivative at 5 is equal to negative 3. So looking at our choices, keeping in mind that it's also concave down, so that might do us some good here. Let's see if we can rule in or rule out at this point. As we go from 4 to 6, it's going down as we go left to right, which would make sense for the derivative being negative at 5 in the middle. True? Are there any where the derivative is not negative? Aren't all of them negative? Okay. So that can't rule any out if they had y values that were going up. Obviously that would be out of the question. Okay. All right. And with that, if we look at the concavity part here, keeping in mind that again, this thing having to be concave down, okay, and with the derivative of negative 3 at 5, if we look at the y values, let's say of the first one, we have 4, 8, and 5, 4, and then 6, 0. If we have those as our 4 points, if we were to do a calculation here, we would have 4 minus 8, 5 minus 4, that would be negative 4 for a slope between these two. If we did the slope between these two, we'd have 0 minus 4, 6 minus 5, would be negative 4. True? And if we did the slope between the last two here, we'd have 0 minus 8 over 6 minus 4, which would also be negative 4. So ultimately, these particular points are linear, aren't they? Okay. And wouldn't the derivative be negative 4? So ultimately, could the derivative be negative 5 at that one? So if we look at choice B here, similarly we have 4, 8. This time though we have 5, 6, and we have 6, 2. And you'll notice that that one is not linear because the difference between 8 and 6 is not the same as 6 and 2. True? And so ultimately with those set of points, our slope between the first two is going to be negative 2, and then the slope between the next two is going to be negative 4. Okay, keep that in mind. So the slope up between the first 2 points is negative 2, and the second is negative 4. So again, this was our work for choice A, choice B. And so ultimately, if it goes from a slope of negative 3 to a slope of negative 4, would at negative 5 be a reasonable thing to have it be negative 3? Sure. Let's think about the concavity part too. Just thinking of a picture here. If I went from 4, 8, and then I went to 5, 6, and then I went from 4 down to 2. Looking at that, if I have that steeper slope right there, wouldn't that be a concave down situation? I drew 2 line segments. It doesn't necessarily have to be linear, obviously, for those parts, but ultimately, would that be conducive to concave down if I decrease more as I go to the right? Okay. So this one seems to be a pretty good possibility at this point. If you look at part C, or letter C, you got it goes from 8 to 6 and then to 5. Okay. So if I went from 8, 4, 8, let's say, and then I went 6, and then I went 5, which would be not as steep a drop. Again, that segment being steeper than that segment, then that would, whoops, stop on the screen here, sorry. If this segment right here is steeper than this segment, wouldn't that be more conducive to a concave up situation? True. Okay. And also, we're going from a slope of negative 2 to a slope of negative 1. Would that make sense with the f of 5 being negative 3? F prime of 5, I should say. So I'd say A and C are out at this point. Looking at D, that's another linear situation. It goes 6, 4, 2. Wouldn't that just be negative 2 the whole time? then finally, if you look at part E, we could use the same argument we just did for C. If we have a slope that goes from 8 to 3, and then from 3 to 2, okay, that's going to be another concave up situation, isn't it? So therefore, which is the correct choice? B. Good problem. Yep.
On 12, you got k equals -1. You said the answer was D.
Yeah, maybe I made a mistake then somewhere. Let's go back and look. What was it? Yeah, you're right. It does say D. Let's go take a look, see if we made a mistake somewhere. I'll fix it. So I got k plus x, bottom, derivative of the top is k, top, derivative of the bottom is 1, k plus x all squared. So on the top we have k squared, kx, minus kx, I see it, there it is right there. Good call. So that right there should be a minus, which ultimately means that's a minus. And which means that's a minus, and that's a minus, and that's a minus. And so ultimately we'd have a -12 over here. So that number right there should have been -12. And so our final answer should have been +3. Good call. Okay. Alright. Others? Through 14. Sorry. And 13, got another table here. And on our table, we just have some function values, looks like. And we have continuous on the closed interval, differentiable on the open interval, which is the start of the mean value theorem, keep in mind. So, might be a mean value theorem problem, might not, we'll see. Ultimately here, though, f has the given values in the table above, and using the subintervals given, what is the right Riemann sum approximation for 5 to 12? So, turns out it's not a mean value theorem problem, it's just a Riemann sum problem, which is an AB problem. And ultimately, if we think about what our picture is going to look like here, if we were to plot those points, we get 5, 10, 6, 7, 9, 11, 11, 12, 12, 8. You know, our points are going to have some pattern like that, basically. And remember, if we're going to do a right Riemann sum, okay, we need to start at the right endpoint, okay, and go up, draw an arrow, or draw a rectangle, I should say. And we'd have those four. Oh, yeah, that's right. So we're going from 5 to 6, 6 to 9. And again, just a rough drawing here, just to illustrate, you know, how those rectangles are going to be drawn. But bottom line is, with our right Riemann sum, if we have a uniform subinterval, okay, we could just write whatever the subinterval length is times all the different heights that we need here. Okay, however, the subintervals are not uniform here, but if we start, I'd probably work backwards since it's a right Riemann sum here. Okay, we know that we're going to take the height at the 12, if you will, and multiply it by the length. It's going from 11 to 12, so we're going to have this rectangle here is going to be 1 by 8, if you will. The next rectangle is going to be measured from the height at 11, which is 12, and it's going from 11 to 9, going in the reverse direction, so that one has a length of 2, so it'd be 2 by 12, that rectangle. The next rectangle would be going from 6 to 9, and it'd be measured at the next height, going left, which would be 11. It has a length of 3. It's the smallest one I drew on here, but again, I'm not drawing it to scale by any means. But bottom line is it's going to be measured at that next height, first height on the right, then going left, 12, and then 11. And then the final height we'd measure here is a 7, and its length would be 1 because it's going from 5 to 6. And so with that, you could add all that up. You get 40 and 64, 72.